my background is mechanical engineering, and I've kind of worked within the engineering and the specification teams primarily. I'm joined today by my colleague Josh Scarf, who is one of our specification support engineers, and again helping to directly support yourselves. So as I said, as Catherine said, if you want to ask a question at any point, please just raise your hand. Someone will then highlight it, and we can ask a question. You can stop me mid-flow. That's not a problem, and we'll leave some time at the end as well. The CPD today is CIBSE accredited, so if you would like a certificate, then I'm sure we can make that arrangement. The subject today is digitising hydronics, building intelligence into HVAC. We'll kind of go through what that means, but fundamentally we're looking at smart valves, delta T control, and integrating within the BMS as well. There's quite a lot of content within the CPD, so again, I'm more than happy to share the slides afterwards to the audience, and if I seem like I'm skipping over certain parts, it's because it's maybe not as relevant to the whole conversation, and I'll pick out the most pertinent bits for the key takeaways. Again, a bit of a background about us. So I'm based in Ipswich, which is our headquarters. This is we've been around in the UK for over 100 years now. We're owned by Crane Co., which is based in Stamford, Connecticut. They were established in 1855, and we also have a manufacturing base in Hitchin as well in Hertfordshire, and a distribution centre in Northampton. So again, more than happy for people to come visit us at our manufacturing site where we make a lot of the products we'll be talking about today. We also have facilities out in the Middle East as well. We're doing a presentation today as a Crane, but as part of the Building Services Group, we also have our Hattersley brand and our NABIC safety valves, of which I manage all of those. And we also have other side parts to the business as well, which is gas and water utilities. As I mentioned, we've been around for a long time, so we do give back to the industry. We're patron members of CIBSE, part of the technical committee on the Commission of Specialists Association, etc., etc. So key part here is we give back, and BCIA is now included in that, which is great. Briefly, what we're going to cover today is have a look at energy considerations. Why are we talking about it? Why is it important? What's the context? Industry opportunities. Again, why are we developing new products? What are people asking for? The part I'll probably breeze through fairly quickly is the introduction to BMS. We do this CPD for a range of individuals, primarily mechanically based individuals rather than BMS. So of course, the audience will be more familiar with that. Understanding valve control is just building up a bit of a history and story as to why we're moving more towards smart technology and the reasons why, including delta T syndrome. Some of the control methodologies that we apply. Installation, digitizing, commissioning, and then we'll look very briefly at the end to some applications. So why do we talk about energy? Well, it's because we use a huge ton. So in 2022, approximately 179,000 terawatt hours of energy, a huge amount. The context is, if you look at how much we use within buildings, 40% of total global energy use is in buildings alone. And that's for lighting and HVAC and everything. More specifically, HVAC is around a quarter of all energy use. The reason we mention this is that if we can find a way to reduce energy consumption within HVAC by even 1%, that is equivalent to a lot of energy. So oil, gas, etc., etc. So the infrastructure change and the impact would be huge. What are people asking for? So these are some of the common themes that come out of conversations that we have with a variety of individuals. So sustainability is key. At the moment, we're seeing everyone talk about this. So how do we increase system efficiency? How do we actually capture how much energy is used in the creation of products as well, the embodied carbon? Again, we're doing a lot of great work there. Occupant comfort. Again, we spend a lot of money trying to create these HVAC systems, and the key reason is to keep us comfortable. Why? It makes us work more efficiently. Automation of processes. We want to reduce the amount of time spent commissioning a system, setting it up, installing it, reduce all of these burdens and costs. Preventative maintenance. So again, how do we identify and fix an issue before it ever occurs? Flexibility. A really good example of this is we design, and we've had a really recent example actually, Cat A fit outs with no idea who's going to be in the Cat B. We install it all, only to find out that the Cat B comes in, walls come up, changes to layout, and half of the equipment is ripped out. A huge waste of cost and time and effort. So how do we create equipment and installations which are much more flexible to those changes? And we're being driven to do this as well. As much as we want to do it off our own backs, we are driven by the likes of schemes set up to drive sustainability and efficiency. The most common ones being BREEAM, and more recently Neighbours as well. And Neighbours is becoming much more relevant within the UK. It's originally adopted in Australia, created in Australia, brought into the UK in 2020. It's now being managed by CIBSE. As I mentioned, we'll do a very brief overview of BMS, primarily because you will all know a lot more about it than I do. So the purposes of this is just to give an introduction to the likes of a design mechanical engineer in a consultant. So I'll be using the term BMS. We all know there's different terminologies that we can use. So it's just a couple of explanations there. And again, smart buildings, we often refer to smart buildings as part of our project, the drive towards smart buildings. What does that actually mean? No one really has a solid definition of that. There's no one singular explanation. So these are some of our ideas. You know, it's building intelligent, it's creating an intelligent physical environment that uses technology to enact efficient and economical use of resources, yada, yada, et cetera, et cetera. And that can be through the use of IoT, the BMS, artificial intelligence even as well. But that's our take on smart buildings. A very, very simplified view of the hierarchy of a BMS, the three main levels, the management, automation, and field. We'll be focusing today on the field devices in the form of the actuators, but it's worth mentioning that the purpose of some of this technology is to simplify the automation level and to simplify the number of components and equipment that we have, and building some of that controller logic into the device as well, rather than simply being an input-output device, actually have some form of logic driving a change. Again, you'll know all about this, but we've got two key types of protocol, open and proprietary. The vast majority of manufacturers now use open protocols. Why? Otherwise, we lock the system down. If for whatever reason that manufacturer was to disappear, then it's very, very challenging to integrate new technology into there. So we're all using open protocol, by which I mean the likes of Modbus and BACnet. Again, there's differences around this. I'm not here to sell the benefits of one over the other. What we do see is that our technology uses both. So we look at both Modbus and BACnet. Some other examples there as well. Talking about Modbus and BACnet, one of the key questions we get is, what if I have a BACnet system and someone's trying to sell me a Modbus device? How do I integrate the two? And we simply explain you use a gateway, a translator. So you can have a series of Modbus devices, field devices on a floor, and then connect them into your BACnet network without any real issue or challenges. So you can integrate these two open protocols together fairly seamlessly. Now, I mentioned here that we want to take a bit of a history lesson, primarily because we need to understand why we have these new technologies, is to understand what we had to deal with in the past and why we've done this continuous development and product creation. So if we go back all the way to control valves, and we still use control valves today, 2 ports, 3 ports, 4 ports, and there's still a place for them as well. There's still a need for them, albeit it is significantly reduced compared to, say, 20 years ago. Typical use of 2-port valves, as you'd expect, is on a terminal device, and we modulate those in response to demand. Now, typically speaking, in a variable volume system, we'd also have other components to help us. Now, on the mechanical side, we'd use something like a commissioning set to help us balance the system. And then we'd have something like a differential pressure control valve. You can see there next to the pump. protecting the system against changes in differential pressure. All of these had to be designed in and considered. We'd also use a 3-port valve, typically either on a constant volume system on all units, or in a variable volume system, we might have one on the end of line. You can see the example there. The key part being is that we want to maintain a continuous flow throughout the system to maintain circulation, minimum pump speeds, etc. So a typical application there. We can also use 3-port valves in applications such as mixing and back at the pumps and injection circuits as well. So there's a place for these. It's not to say that we no longer need to use them in any capacity, but it is far more reduced. 4-port valves, a bit more specific, a bit more niche, is typically on fan coil units where we've got a 40mm pitch between flow and return. So does a 4-port valve, and we can fit it directly over a drip tray. Same application as a 3-port valve. We'd use that for minimum flow circulation and minimum flow in the pumps. The issue being is that with a control valve, if we're using it in the application of serving a terminal device, needs to be sized. Every single one needs to be sized. And what I just want to briefly show you as an example, if we look at this, so I've got the different, let me do the pointer, that will help. I've got the differential pressure across my coil, and I've got the my 2-port valve here. The aim for the 2-port valve is to have the same pressure drop as the coil at design load. We can represent that in this simple calculation. The dP over the control valve divided by the control valve plus the coil equals 0.5. That's the target. That's what we want. The reason being, valve authority, as the 2-port valve modulates, we actually get a response in the system. If we have a very poor valve authority, what we'll have is a modulating valve which does nothing until it shuts, which is not the most energy efficient solution. So we need a reasonable valve authority, in this example, 0.5 in the context of control valve and coil. How do we achieve that? So let's take an example. I've got a flow rate, design flow rate based on heat load of 0.2 litres a second. Based on that design load and how I've selected my fan coil unit, the differential pressure across that is 15 kPa. My target for the control valve is 15. I use this calculation here to determine what my KVS, the valve coefficient, should be. 36 times flow divided by square root of delta P. Plug in the numbers and I get a theoretical 1.9. That does not exist. There is no valve with a 1.9 kV. So what do? We find the closest match. In this example, 1.6. I then have to reverse the calculation. Now, this is all built within Excel usually, and it can be automated to a certain degree, but I still have to do it. So I didn't quite achieve 15 kPa based on my KVS of 1.6. I've achieved 20. So my valve authority isn't quite 0.5, it's 0.58. The key takeaway here is that there's always a compromise when selecting 2-port valves. They're never perfect. And I have to complete this exercise on every single one. Not only that, but when it comes to actually balancing the system and commissioning it, my 2-port valve can't do that. All it can do is be sized for the given flow rate and the pressure drop. It has no other intelligence built within it. So to balance my system, I still have to use these commissioning sets. And I typically have one on the floor, on a sub-branch, and on all of the individual terminal units as well. And some poor soul has to go around and individually balance all of these. And they have to balance a branch, the next branch, 2 branches against one another, a floor, the 2 floors against one another. It's a laborious and time-consuming process. So to a certain degree, the reason I've explained that is to highlight the issues that not issues, but the concerns, the difficulties, the challenges we might face when using control valves. A typical standard 2-port control valve. We need to understand the valve authority. We need the equipment information. If we don't have the flow rates and pressure drops, we're second guessing ourselves. It's never perfect. It's a best fit. It's time consuming to balance the system. Subject to flow variation as the pump modulates its speed. If we don't put in things like DPCVs, it's little to no intelligence, and sometimes when we do need to use them for zone or end-of-line bypasses. Which led to the creation of PICVs. PICVs have been around, this is a pressure-independent control valve, for 20 plus years now. I would say the adoption of these has been really in the last 10 years, kind of market maturity in the last 5. So very, very commonplace now. Why did we create a PICV? Again, summarizing quite a lot of information here in a couple of slides. We have a 2-port valve on every coil. We have a balancing valve on every coil, and we have some form of differential pressure protection on every branch. It could be somewhere else, but on every branch. The idea of a PICV is it removes all of those. We don't need them. They're not required, overcomplicated, costly, time-consuming, and we replace it with a single device. Now, a PICV has a diaphragm within the valve itself, so it can be pressure independent. It has a regulating feature, so it's my regulating valve, and I can screw an actuator on the top, so it's my 2-port valve as well. So it massively simplifies the system. One of the issues I highlighted before with 2-port valves is that you needed to go around and balance everything off in a systematic process. With a PICV, I can set the flow rate on the dial, and I can do it independent to any other coil on the system. So again, I'm speeding things up here. I'm simplifying the system. I still have to set that dial. I still have to climb a set of ladders, try to find that dial, and then turn it to a number which is, for the best will, quite hard to see in a dark ceiling void. So I still have to do that manual process. I've improved things, but still not perfect. And I still have to put an actuator on there. So some typical examples of the actuators we tend to come across in the market today. So you've got a modulating actuator on your left-hand side. That can be fairly quick acting, 8 seconds per millimeter. It's a 4mm stroke, so we can close it in half a minute. Can control on a 0 to 10, a 4 to 20 milliamp. But configurable dip switches, again, physical dip switches. I have to open up that actuator to change a dip switch, i.e. from direct to reverse, linear to equal percentage, 0 to 10 to 5, 0 to 5, etc. It may have some form of gap detection built within there, and it can be configured with feedback and fail-safe. And then we get to the slightly less intelligent ones. So we've got a floating type actuator, a bit slower to react. And then we've got the lowest cost option, let's call it, of a thermal actuator. Again, very slow to react. Typically, you can have 0 to 10 volts. I wouldn't personally choose that, but typically on off. And therefore reacting in a wider room temperature variance as well, a wider band. The most intelligent it gets with this is that feedback feature. Other than that, it doesn't give us much back into the system. And as I said, that's been used quite regularly over the last several years. But how can we, of all of the things I've just mentioned, how can we make things easier? How can we reduce the burden of someone turning hundreds of dials? In some projects, it's 2,000. How do we reduce the burden of people going up and down ladders to set those? How do we reduce the burden of issues happening in the field and we don't have any visibility because the data is not being captured? And this is where we start to look at intelligent valves. So what do I mean by an intelligent valve? So fundamentally, what I've got is something which has got information stored within there, has its own control loops, it has its own intelligence. Typically, you might find that within here, they're BMS enabled, so we can talk via Modbus, in some examples via BACnet, and we can access a huge amount of information. In this example, the valve information is built within here. So I can select via one of the Modbus registers what valve I'm connected to. And when we think, what's the benefit of that? For any given valve, I've got my flow rate information built in there as well. So I can select, say, a 2-inch PICV that I'm connected to. I screw it onto a 2-inch PICV, that one in the middle. And when I say I'm on that PICV, it'll give me the flow range. I input the flow range on a separate Modbus register. The valve will drive to that flow. I didn't have to physically touch the valve in any way, apart from screwing the actuator on. I don't have to go to it. I don't have to check it. All I have to do via the BMS is set the flow rate. Going back to the example of the Cat A, Cat B fit out. So we've actually got some of these installed in a project in London. They did all of the Cat A and now they're doing Cat B, and lo and behold, the flow rates have changed. The process for them updating those flow rates is going on to the BMS and inputting a new value in the required Modbus register on a couple of dozen valves. That exercise itself can be completed anywhere from a few minutes to a couple of hours. It's not a long process. And without anyone having to physically touch the valve. No step ladders involved, no access issues. All of it's connected and already pre-configured because it's already been installed as part of the Cat A. As well as that, all of those dip switch settings that I mentioned before, the direct to reverse, the equal to linear percentage, all of those are now done via a register. There's different registers for all of these. We can find the dip switch settings effectively built within there. We can also get separate registers to give us flow rate based on positional feedback. So all of this information is now at our fingertips. And as I'll show you in a moment, we can now gather even more information with versions which have temperature sensors connected to them as well. So now we can generate information such as flow temperature, return temperature, delta T. Now that I have power, now that I have flow rate, and now that I have delta T, I can generate power. So effectively, I can use these as a form of heat meter. And all of that reduces the amount of components, complication, setup that we have within our system. So this is the digitized and hydronics bit. And other benefits such as reduced cabling, because I can daisy chain the units together as well. We can go up to around about 7 or 8 units daisy chained before we have to integrate another power input. Now, I can't physically do an example here because we're doing it via Teams, but you can see some of the examples of what the tool might look like on the right-hand side. And I can go on the next sheet and show you some of the live examples here. So this is a configuration tool that you can download from our website. These are just effectively all of the Modbus registers in a nice, easy-to-use format. So we don't have to go looking for the register and what values I need to input. We do have all of that information on our IOM. This just simplifies the process. And you can see it's as simple as a drop-down box. So I can switch it from direct to reverse acting. I can select the valve type I'm on, that all stored in here, and I can input the flow rate. It even tells me what the minimum and maximum for that valve is. And to set the flow rate, it's no harder than just typing in the number here, hitting enter, and the valve instantly responds, and it sets its new flow rate in approximately 10 to 15 seconds. And I can do that en masse. I could set it up so that I can send all of these values to all of the actuators individually addressed, and setup can take minutes rather than days and weeks. I can also get some feedback information via the actuator as well. As we all know, Modbus tables can be long, complicated, and challenging to read. So what we've done, because we typically size the PICV and the valve, is we have all of the information such as flow rate, such as size, such as range, and we can input that into a selection software, and we can get it based on those values to generate the required numbers under the Modbus addresses as well. So if I was to give an example, and I've just picked some random valves here, PICV number 1 to 10. If I needed to input a flow rate of 0.2 liters a second, I now know that PICV number 1 under address 6148 needs a value of 200 via the BMS. Valve number 2 requires a value of 100. I can select what my valve operation is. These are a series of drop-down boxes. If I change it from direct to reverse, it changes the bit here, and I can generate a new output. So this is my actuator setting under address 6689. Speed, valve catch, the baud rate, all of these things I can configure and already have preset, in the sense of I can provide all of this information without having to look through the Modbus tables individually. So what does this mean? Well, I mentioned about going up and down a set of step ladders all of the time. And we often have to do that multiple times as well. Once to turn the dial on the valve, another time so someone can actually put the actuator on the valve, another time so someone can measure the pressure drop across the valve, another time because it wasn't quite right that time, so they need to go back and adjust things slightly. So we can reduce the number of these ladder events quite significantly. We don't have to do any of the manual dial setup on the PICVs. It's all done remotely now. Often, this is one of the biggest issues when we're working in hard to reach locations. And give an example of the Cat B fit out, all too often I've come across a fairly new building and they've completely concealed access to any of the valves or equipment. You just can't access them. So we can remove that issue, the number of revisits, and this time-consuming process of setting up dials, going to each valve, etc. I can now work comfortably from a safe environment. Flow rates can be set not only remotely but en masse. I can change actuator settings. Another example of that is the actuators come as default direct acting. Quite often people will want to change that to reverse. All of these are installed and they don't realize that until they're up in the ceiling void, which requires someone to go up, take the lid off the actuator and change the dip switch. But now if I discover that, I can access the required register and I can send the new value to all of them and fix that issue within seconds, rather than days of someone going up and down ladders and getting in the way of someone else trying to do other commissioning and setup in that space. So we can reduce some of that burden that's currently experienced.
I think you've got a question.
Oh, go on, Ron.
Hi there. I see lots and lots of the benefits of this, but with your register and changing the flow rate, are you changing the stroke length, or do you recalibrate the actuator itself so it has full stroke, still 5mm stroke or whatever it is?
Yeah, really good question. So the way it works is we deliver the valves and we test all of the valves at the full stroke, which is in this case is 4mm. So the valve arrives at fully 100% open and should not be turned. You shouldn't touch it at that point. The actuator is put on, and when you input the flow rate, it adjusts for the new valve stroke. So a very simple example is if at full stroke the flow rate is 0.2 liters a second. If the design is 0.1, it will change the stroke from 4 to 2 mil. And it will drive the 0 to 100% command from that new point. So it will drive to the positional flow rate on the stem. So it will adjust the stem stroke, and it completes a calibration every time you do that as well.
Okay, so how much does that affect the rangeability, say, of the valve and the the fine adjustment of the valve itself? Yeah. So it doesn't change it from the way that we traditionally set them up now, in the sense that we have a reducing stroke PICV. So even if we needed to do it manually, you adjust it and the stem stroke reduces. The rangeability is driven primarily from the actuator itself. So we're still driving it not to 100%, albeit, yes, on a shorter stroke length. In theory, it shouldn't cause any issues. We still have 100 to 1. We can drive it in 1% increments, etc. But on a reduced stroke length. So you wouldn't expect the same level of granularity had it been at maximum setting. Yeah. Okay.
Yeah. But what we can do is we can plot and we can show, I haven't got examples here, but if you're interested, we can pick it up separately. If we set it to a reduced stroke length, I'll pick 50% as an example to define that design flow rate. We then drive that valve from 0 to 10 volts, so 0 to 100%, and watch if we still maintain that equal percentage curve, which in this case we do because the algorithm's built within the unit. So still maintain that rangeability at reduced strokes as well.
Thank you.
Problem. So getting on, so building more intelligence into the system. What we also have is more issues as well. So delta T syndrome is a major one. I'll give a recent example of one which we came across. We're up at a university, quite a large estate. In fact, they have multiple estates, all running off heat networks. And they were showing the system, the live BMS feed. And going into the building was 80 degrees Celsius for the heating system, and coming out was 78. So a horrific delta T issue. Something was happening that it couldn't dissipate the heat. There could be multiple reasons for this. Poorly designed system is usually the main one, but poorly maintained systems as well. We could have systems which aren't installed correctly, so bypasses are open, so the heat just isn't dissipating. We could have blocked coils over time as well, and all of these lead to this delta T syndrome. Now, what does that mean is if we have a reduced delta T, in order to generate the same power, the only thing I can really do
is increased flow rate. Now, this is critical to the next part, because as I increase flow rate, I'm obviously generating more energy as well from the pump and from my for the power required there, just to achieve the same heat output to the user, assuming specific heat capacity is a constant anyway. So it's only a factor of Q flow rate and delta T. Now, with a standard 0 to 10 volt control on a valve which has no delta T or temperature intelligence, it is purely going off the basis that it believes the position it's in is generating the flow rate it's designed for. When in reality, the flow rate may not be generating the power because the delta T is compromised. So it's one of these chicken and egg scenarios. I can't fix one without knowing the other. To give another example, if we have a look at this graph, if I increase flow rate along the x-axis from 0 to 100%, and then if I plot delta T in red and I plot power in blue, we get this type of effect. So it stands to reason that when I increase flow, I increase power, as you can see in this graph. The downside to that is, as I increase flow rate, I have less time for the heat to transfer across the device, and my delta T goes down. And then we get into, in this example, above 60%, this kind of loss zone, where I'm generating very little power increase because my delta T hasn't really changed at that point. So I'm generating more flow for little to no benefit, which doesn't really change this scenario here. So how do I prevent myself getting into this zone? What we traditionally have are systems which, and we can do it, and we can do it with heat meters, etc. We can do it with temperature sensors. We have systems that can monitor it. And that's about as good as we do usually. So we monitor the situation, and then we eventually get a report that tells us delta T is poor or power output is compromised, whatever reason. And what we're saying is that that's not good enough. What we need is a system that can not only monitor the temperature, monitor the delta T, and monitor the power, but correct itself when it sees things aren't going right, and can maintain a value to protect the efficiency of the plant room. So you can see an example here. This is just a larger setup. So we've got, this is an electronic PICV driven by pressure sensors, pressure transducers, you can see there, P1, P2, and by temperature sensors as well, T1, T2 installed on the pipework. T1 is flow, T2 is return. And what I can now do is monitor and control based on these. These are separate Modbus registers, both T1, T2, and the resultant DT. We can then generate power based on positional feedback. That's a separate register as well. So we can use this as a form of heat meter, albeit not a billable one in the sense that it's not MID approved, but then applications we're talking about are going on to, we've seen examples on heat pumps, on AHUs, even on individual terminal coils, where we wouldn't necessarily bill, but we do want to get that energy information out of the system. So now, not only can I use these registers to monitor the values, if I set a limit, and we'll get onto this in more detail in a moment, if I set a limit, i.e. I set T2 to 12 degrees Celsius, let's assume it's a chill system, I can set it and the valve will automatically control itself to ensure that the return temperature is always 12. So it won't compromise on the delta T if the valve is being driven open to generate what it thinks is more power. In reality, it's just wasting energy. So I can set that limit. I can set a limit based on delta T. I can set limits based on power, because all of that information is now built in. And going back to my point at the beginning, the logic is built within the field device itself. So a traditional way I would have done that is I would have separate temperature sensors. They would report the information back via the BMS. A logic is created in the BMS to use that information to drive a command to the valve to compensate. No one does that because it's overcomplicated. So we just leave it to drive 0 to 10 volts, thinking it's doing what it should be doing. So all of that is now built within here, which leads me on to the control methodologies. Flow management is a traditional one. So we think we're driving based on flow. We're actually driving based on position. Now I'll talk about that in a moment. We then move on to, because I now have this powerful information in the form of delta T and I can generate power, I can now manage my control based on power, based on delta T based on return temperature management. I'll show you examples of those. So this is our traditional 0 to 10, 0 to 100% control here based on what we believe the flow output will be. So here's my heat output from the coil. It's this kind of shape. My valve usually is equal percentage. It's doing the opposite. So I drive 0 to 10 volts on a nice linear resultant curve. The issue here is that when it drives, the position it believes it's in is generating a flow rate to give us a power output. If, for example, my delta T is significantly compromised for whatever reason, blocked coil, some issue elsewhere in the power generation, despite the fact it thinks it's generating a power output based on the flow rate, it's not. So it'll be generating a flow rate without any real indication that the user's getting the required heat output. But now, if I have delta T as a factor, as a value, if I have delta T and flow rate, I can have power. So now I can drive based on power. Let's say my device has a power output of 5 kilowatts. Let's just pick a number. I can now drive a 0 to 100% control signal based on a target of 5 kilowatts, which means it's constantly compensating flow rate and delta T to achieve that power. So if there is an issue with delta T, it will compensate by delivering a higher flow rate to give me my nominal power output. But we can go one step better than that. We can actually say, if I maintain my return temperature, then I can maintain my power and I can protect my plant at the same time. So how does that work? Let's take the example up here in a heating system. So I've got my supply temperature, slight variation there, and I've got my return temperature based on these T1, T2 sensors. If I set a limit, you can see that's this line going along here. If I set a limit, the system will ensure that as the temperature was due to creep back up, so my delta T would be poor, the valve will take over control from the BMS and reduce the flow rate. And it will reduce the flow rate to create a better heat transfer to maintain that return temperature, or at least so it doesn't go above the limit. And it'll do it automatically. All I have to do is set what that value is. And to use an example, if it's a heat pump system, a 55-degree flow and a 45-degree return, if it creeps up and it starts to look like 46, 47, reduce the flow rate, maintain that 45 degrees until it falls back below, so you get a good delta T. Once that is satisfied, BMS control goes back. And this is all automatic. All I have to do is input that return value. So I'm protecting things like the heat pumps, which are quite precious over the temperature that they get back and their delta T's and return temperatures. I protect the system from delta T syndrome as well. And I can monitor all of this information on a continuous basis to see if there's any trends that I need to investigate as well. Let's look at some quick applications, conscious of time, and then leave enough time if there's any queries at the end. It doesn't have to be huge, bulky, and expensive. So we can use these types of solutions on devices as small as 15 mil fan coil units. I'm using fan coil unit as an example here. And I don't have to have huge ultrasonic flow meters, for example. I don't have to have huge rotary control valves. In reality, what I want is a system that can control flow rate while monitoring delta T to generate this power. And you can see an example here. So we have a compact valve set. This is known as our Dominator Eco. We've got a PICV built within this section here with an integrated bypass. Some test points here if someone really does want to measure flow rate or pressure. And what we have here, traditionally, we have flushing valves used as part of the commissioning process. We've got an adapter in here, which allows us to put the temperature sensor in. It's a contact temperature sensor. So now I've got T1 and T2 feeding straight back into this smart actuator with the inbuilt logic in there. And all of this can fit on an A4 piece of paper. So it's a very compact solution generating this heat meter output. And of course, you can scale it up as well. So on larger installations with larger flow rates, we can do valve sets which go up to 1 inch in size. But again, we're utilizing existing drain valves with adapters so that the package size doesn't get huge. And usually we've got plenty of space. So yes, the actuator gets larger, but in itself doesn't take up a huge amount of space. There's usually plenty of room for that. So again, we're not making the system cumbersome, but we're generating this energy meter output via the BMS. It's a separate register. And again, we can scale it up from here. So the previous example I showed was the larger flanged smart valve. So again, we've got pressure sensors here, but we've also got our temperature sensors. And again, we just locate those into the flow and return of the pipework. And I can do the same thing, the separate Modbus registers, where I can set my return temperature limit. I can set my delta T. I can set my power. I can monitor my power, which means that in this example on an air handling unit where I may have traditionally had a flow meter, I saw a heat meter with its temperature sensors. I no longer need that now. I can get rid of it. It's all built within this. So while this technology itself is generally a higher cost compared to a 0 to 10 volt actuator, say, the cost difference, once you take into account all of the other components you do not need now, if not cost neutral, will be a cost benefit. Plus, you get all of the operational benefits from the valve controlling based on temperature, based on power. So you get operational efficiencies. The very last slide is just an interesting live example that we worked on. So we were requested to support in a project where they were installing heat pumps, and the heat pump delta T was tiny. It was 5 degrees. In this example, they were going out at 55 and returning at 50. That was the requirement. The problem was that the system was designed around a delta T of 10. So it was going out at 55, but it was coming back at less than 50. It was coming back at 45. And they had very specific instructions from the heat pump manufacturer that it must come back at 50. So what they ended up doing is installing a solution where these valves were used to monitor the flow and return temperature. And if this return temperature was set at 50 via the valve, and if it dropped below 50, it was configured that the valve would open, bleed in some of the flow back into the return to top up this temperature from the 45 degrees. Now, it's a bit wacky, this example, because we're effectively generating energy to try to save the heat pump, which seems like a bit of a waste. But we've seen quite a few examples of this being used because of the unique setup of some of these systems. But we came up with a solution, and the application suited the client, the consultant, the contractor, and it worked as well. So we can find somewhat unique applications for this type of technology as well. It doesn't just have to be on traditional terminal units where you may expect to find a control valve. With that, I'm done. Thank you very much. So were there any other questions as we were going through that? And no worries if not, you can always contact me separately.
Any questions from anybody?
No, I couldn't have done it better myself.
Oh, you're too generous, Nick.
If there aren't any questions, just to confirm, obviously the video recording of this and the slides, we'll send it round to you as attendees anyway. You can always access it through the members portal and on our YouTube channel as well. Obviously Neil's contact details are there, so they'll be sent to you. But if not, it's your last chance now to ask any questions from what you've heard. No? Okay, in that case, Neil, thank you very much for giving up your time, and we will we'll send. Oh, there we go. Very informative. Thank you, Neil. Thanks, Daniel. So yeah, that's perfect. We will we'll share the information, and hopefully you've learned something from today's session as well. But thanks very much, Neil, for giving up your time.
No worries.
Cheers.
Really good. Thanks for all your time. Enjoy the weekend.
Thank you all.
Thank you.
Thanks. Bye bye.
Cheers. Bye.
Thank you. Bye.